Padua, March 12, in the year of our Lord, 1610. To the most serene Cosimo II of Medici, 4th Grand Duke of Tuscany. Great indeed are the things which in this brief treatise I propose for observation and consideration by all students of nature. With the aid of a spyglass which I devised, after first being illuminated by divine grace, I discovered that the moon is not smooth and polished, as some philosophers believe it to be, but is in fact rough and uneven, covered everywhere with huge prominences, deep valleys and chasms. Perhaps other things, still more remarkable, will in time be discovered with the aid of such an instrument.
Telescopes were really our most effective tool for studying the moon for over 300 years. It was evident, even to early observers like Galileo, that the moon has two main kinds of topography. There are the so-called maria, or seas. They're large, relatively flat, and smooth plains that can be seen from Earth with the naked eye. And there are the highlands, the rough, relatively light-colored and heavily cratered areas that surround the maria. But even the best Earth-based telescopes can't distinguish objects smaller than a large football stadium on the surface of the moon because of interference from the Earth's atmosphere. To get closer, to get a really good look at the moon's surface, we had to wait for the development of spacecraft. And that's when we discovered that the moon's entire surface, including the seemingly smooth maria, was covered with craters, some of them less than a centimeter across.
Video still good. Excellent signal strength. 3, 2, 1. Impact.
Now it is time to take longer strides. I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
I present. Mode control both auto, descent engine command override off. Engine arm off. We copy you down, Eagle. Tranquility Base here. The Eagle has landed. I'm going to step off the limb now. Surface is fine and powdery. Look at this. Tony, this is a black matrix with some excellent crystals in it.
What do you think of this thing here? It's kind of translucent. Yeah, translucent down the other one to get a... Yeah, when it rains.
It's very difficult to describe to you our tremendous excitement at the opening of the first rock boxes and the preliminary examination of the samples from Apollo 11. Although we had very good data from complex spacecraft such as this surveyor here beside me, there's no substitute for having samples in your own hands, in your own laboratory, in your own instruments, where you can examine them much more rigorously. The importance of these samples is that they give us our first information from the surface of a second planetary body, so that we can begin to compare the processes that go on the moon with those that go on and within the Earth. Only 250,000 miles separate the Earth and the moon in space, yet look at how different they are. Now that we actually have samples of the moon, we are hoping that we can answer questions that we've been asking for a long time. Questions like, how did the moon originate? Obviously, there's a difference between the rocks that make up the mare and the rocks that make up the highlands. But what is the difference? What processes have shaped the surface of the moon? Was there ever water on the lunar surface, or even life? Why is the moon so different from the Earth? Much of the geologic history of the moon is locked up in the lunar rocks, and it's that record that we're now trying to read.
This is rock 12,064, a volcanic rock picked up by the Apollo 12 astronauts in the Ocean of Storms. Has a texture very typical of a quickly cooled magma. As you can see, the cleavage is reflecting off the 3 millimeter by less than a millimeter wide layers. The feldspar are long, thin, white grains, and you get nice reflections from the feldspar grains as the cleavages come in to catch the light. It's very much like terrestrial basalt poured out on the surface of the Earth and cooled rapidly.
You may wonder, how can we be so positive about how a lunar rock formed when nobody had ever seen one before, and when even now we've seen so few of them? Well, we already know a great deal about how rocks form here on Earth, and we can apply that knowledge to rocks that came from the moon. This area around here, for example, is a lava flow. It's a type of volcanic rock we call basalt. Now we can take a look at this rock right here in the field and see in it certain features that tell us that this rock is volcanic. Size of the crystals, for instance. When we look at a fresh surface, we can see a few small crystals. They're the white grains that reflect the sunlight. However, most of the rock consists of crystals that are too small to be seen, even with a hand lens. In fact, much of the rock is volcanic glass. Usually small crystals in a rock like this are a sign that the molten rock cooled very rapidly. And that's, of course, exactly what happens near the surface of a lava flow. Now compare the size of the crystals in this rock with the size of the crystals in the rock from the lunar mare. A lot of volcanic rocks also have vesicles in them, little holes that were formed by gas bubbles that escaped while the rock was still molten. We find the same kind of vesicles in many rocks from the lunar mare. So we can feel pretty certain that this moon rock had a volcanic origin, as did our basalt here, just from looking at the hand specimens. And of course, there are other techniques to confirm that.
Another technique used in the study of rocks is to prepare thin sections which allow light to pass through. This is a thin section of the same terrestrial basalt we just saw. Polarized light clearly reveals the different minerals of which the rock is made. Notice that, in general, the crystals are fairly small. Also notice the large number of crystals with light and dark gray stripes. These are crystals of feldspar. For comparison, here's a thin section of the rock from the lunar mare. This rock, too, is composed mainly of feldspar. But more important, the crystals are about the same size as those in the terrestrial volcanic rock. More evidence that the moon rock is also of volcanic origin. Of course, knowing how a rock was formed reveals little about when it was formed. Yet to scientists trying to piece together the history of the moon, it was important to determine just when the various rocks were formed. To find out, many rock samples had to be painstakingly analyzed. It turned out that the oldest mare rocks are about 3.9 billion years old. The youngest, about 3 billion years, older than all but a few rock formations on Earth. The Maria, then, are ancient lava flows that flooded vast areas of the moon. The origin of the rocks in the highlands has been more complicated to unravel.
There you go. That's a good rock. Hey, look at the pits in it, too. That's just going to be a good
That's
rock.
because almost all rocks found in the highlands have been changed dramatically since their formation. Rocks from the highlands typically look like this. They're made of the bits and pieces of various other rocks to form a rock type called breccia, a word meaning broken. Look at a breccia under the microscope, and you'll see that the whole rock is a jumble of jagged and broken pieces that are held together by a dark material. Even individual fragments within the rock are full of cracks and fractures. The cause of this disorder? Meteoroids slamming into the moon many times faster than a rifle bullet. Each impact digs up a large quantity of rock. Some of it melts from the intense heat produced by the energy of an actual meteoroid impact. Rock fragments mix with the molten rock, which then cools, hardens, and forms the breccia. Even the smallest particles found in the lunar soil, some so small they have to be viewed through an electron microscope, have microscopic craters caused by still smaller meteoroids. Is it any wonder, then, that hardly any pieces of the moon's original crust survived a fierce bombardment from space? Here's a fragment from the lunar highlands which may have been part of the moon's original crust. The rock is made entirely of intergrown crystals, and the crystals are much larger than the ones in rocks found on the lunar Maria. What accounts for the difference?
This mountainous area on Earth is like the highlands of the moon in some respects. It's another place where we can get some clues about the origin of a lunar rock by looking at an Earth rock. The entire mountainside here consists of a white rock called anorthosite. You look at the rock more closely, and you'll see that, just like the moon rock, it's made entirely of intergrown crystals. And some of the crystals are rather large. Geologists generally agree that for these crystals to grow this large, molten rock must have cooled deep underground and over a very long period of time. We can therefore conclude that the lunar highlands were also molten at one time, and that they too cooled very slowly. The highlands were probably the earliest rocks to form on the moon, because the oldest rocks from here date back about 4.5 billion years. When scientists compared the chemical composition of rocks from the highlands and Maria, they found that both are composed mainly of slightly different proportions of the same 5 elements: silicon, aluminum, magnesium, iron, and calcium. The similarity in chemical composition is reflected in the rocks themselves. In the rock we saw a few moments ago from the highlands, the most common crystals by far are the striped feldspars.
The same is true of the rock from the Mare, only the crystals are smaller because the rock cooled much faster. Both rocks seem to have come from the same basic material, and both highlands and maria were once molten. To melt such vast quantities of rock, a tremendous heat source must have been present inside the moon. Scientists wondered whether the moon's interior might still be hot or molten. To find out, several seismometers were set up on the moon's surface. Seismometers detect and measure vibrations caused by moonquakes and meteoroid impacts.
Now we're picking up your heavy footprints going by the seismometer.
Signals generated are radioed to Earth for analysis by computers. Thousands of moonquakes have been recorded, most of them very small compared to earthquakes. The clues about what the interior of the moon is like come from the different kinds of waves moonquakes produce. The first waves to arrive are called P waves. P waves can travel through both solid and molten rock. A short time later, another set of waves arrives, called S waves. Unlike P waves, S waves cannot travel through molten rock. The difference between P and S waves became of great importance when scientists analyzed the records of the same moonquakes taken by different recording stations. Here, both stations recorded P waves. But at the second station, no S waves showed up when they should have. What apparently happened was this. A moonquake took place somewhere on the backside of the moon. The recording stations were scattered on the front side. Only one of the recording stations was in line with the center of the moon and the place where the quake occurred. As the P waves passed through the center, they were slowed down slightly. But the S waves that passed through the center were absorbed altogether, and only S waves that missed the center reached a recording station. This must mean that the moon has a core that is still partly or even completely molten, like that of the Earth. So we now have a fairly clear picture of the moon's history. The moon's geologic clock started running about 4.6 billion years ago, about the time the solar system was forming. At that time, the moon was probably molten to a depth of several hundred kilometers. As the molten rock cooled, different kinds of crystals formed. The more dense ones settled toward the bottom, while the less dense ones, especially feldspar, floated toward the surface, forming layers of different types of rock. The moon's highlands are probably the battered remains of the original crust. This crust must have been formed in the first 100 or 200 million years of the moon's existence. Meteoroids, some of enormous size, bombarded the moon from the very beginning. The heavy bombardment continued for several hundred million years. Then it died away very rapidly, and a new phase in the moon's history began. Portions of the moon's interior melted again. Some of the molten rock poured out onto the surface, filling the basins created by impacts and forming the maria. Then, about 3 billion years ago, the lava flows too seem to have stopped. And since then, Since then, the moon seems to have changed very little. An occasional impact of a large meteoroid and a continuing rain of small ones. But other than that, the moon's geologic history seems to have ended when life on Earth was just getting started. And that's how humans found it. We have walked on the moon, driven across it, poked it, sampled it, scattered instruments on it, and organized the largest single research program in the history of science to try to understand it. Yet it still hides many of its mysteries. For example, we may never know how the moon originated, because its earliest record has been destroyed by the impact of meteoroids. Which raises a question. If the moon was so heavily bombarded, why wasn't the Earth a much larger target? Well, look up into a clear night sky, and you'll see that small meteoroids, shooting stars, constantly bombard the Earth. Most of them burn up in the atmosphere. Only the larger meteoroids actually reach the ground and leave recognizable impact scars on the face of the Earth. So far, fewer than 200 impact craters have been found on Earth, most of them fairly young. Why so few here, when there are so many on the Moon, on Mars, on Mercury, and probably on other planets as well? The Earth is a restless planet, in constant change, even to the rocks themselves, whose rate of movement is measured in the thousands of years. And so the Earth has erased the scars of the early bombardment. And these qualities make the Earth unique. Earlier we asked, why is the Moon so different from the Earth? Perhaps we should ask instead, why is the Earth so different from the other bodies in the solar system?